right, I'm sitting down with Paul. How you doing, Paul?
Hello. Good. Good to be here.
So today's topic is gonna be a little bit different. I've been doing episodes mostly for like people who are like junior devs who like just got their first job, but I wanted to look at it from a different direction, like people who've been working in the field for quite some time, and to open it up because me personally, I don't do what you do. Like I'm a web developer. I deal with like React and websites, but you do like more data science, right?
Yeah, absolutely. Yeah, so my career trajectory has been interesting. So I got out of academia about 8 years ago, went into data science immediately, did data science for 5 years, became a product manager for 2 years, which was an interesting shift. Recently, at the beginning of this year, I became a machine learning engineer, which is like data science but different.
Everyone wants machine learning, right? Everyone wants their two scoots of machine learning for whatever it is that they're doing. My coffee maker wants machine learning. You
Absolutely.
know, my
Machine
refrigerator,
learning all the way down.
everything needs it. Would you still say you fall in the umbrella of data science, or do you feel like it's more, like you said, it's more specialized now? Like, how would you differentiate the two if you feel that one's more specialized than the other?
Yeah, so this is my take on it, which, again, I don't have the authority to make any proclamations here, nor is there any kind of authority that I can draw from, so this is just my opinion. Data science, in my opinion, is, broadly speaking, the application of science to business problems. That's really what it comes down to. People have been applying science to business problems for a lot longer than data science has been a job.
Sure.
And the reason why data science is now a job is because it requires a lot more skills than it used to. So, for example, in the 1970s or something like that, you might have had a company where you've got like some sales data, maybe you've got like 100 customers. You would sit down and actually think through that data. Maybe you'd plot some linear regressions or something like that. You would be like making hypotheses about what you could do to affect those sales numbers, and then you would test those hypotheses by building a model, making some forecasts, and then checking and see if those forecasts are actually correct. And that wasn't hard. Like you could just do that with your pen and paper. You could do it very informally. There's no need to be very buttoned up about it. What's happened, I think, in the last 20 years is computers have become more powerful. Data warehouses, databases have become a lot cheaper. And so companies, just as a matter of course, have been recording a lot more data than just like your last 6 months of sales data for 100 customers. The big tech giants, Google, Facebook, and so on, they're recording every bit and byte of interaction that you have with their websites and all that.
Oh yeah.
So it's just astronomical amounts of data. Even if it's not your product, even if you're a marketing department in a consumer goods company, maybe you're going out and you're buying a bunch of data, like you're buying social media data or you're buying sales data or whatever it is. Basically, what's happened is there are enormous data sets now that you can use to make business decisions that weren't available, and therefore you need specialists, people with the skills not only on the statistics and modeling side in order to draw rigorous scientific conclusions from those data sets, but also engineering skills to work with data sets of that magnitude. That whole umbrella of things is what I would call data science. But machine learning engineering is a corner of that problem that's emerged even more recently, like really within the past even 5 years, I would say, the following. So we've got all this data, and we want to solve some problems with this data. So the normal kind of problem you would solve with this data would be like you would take some time series data and do some kind of regression, or you get some like more routine insights, count how many times people have used the word angry in your customer complaint data set or something like that. You wouldn't need to traditionally have some really sophisticated model that's finding really fine-grained signals. You just be doing coarse, large-scale quantitative insights out of these data sets. But recently it's become possible to get really nasty with your analysis. We've got machine learning models now that can pick up subtle meaning in the language that people use, identify emotional context based on their word choice. We've got models that can analyze video and images to look for what objects or actions or scenes or emotions or whatever are present in images. We've got like Bayesian models and that sort of thing that can confer causal relationships between variables in large economics data sets and combine lots of different data sets together and so on. And so that the models that you need in order to extract these much more complex signals are just much more complicated to implement and to run in production systems than like running a linear regression or logistic regression or doing a chi-squared test or whatever statistical technique you want to talk about. And like the discipline of machine learning engineering has emerged essentially as a reflection of the fact that building, running, and maintaining these models requires its own set of specialist skill sets within the space of making business decisions using data in general. So that's it. That's how I'd break it down.
Okay. So here's the thing. Because it has a lot of mystery surrounding it, right? Because people only see the end result of things, right? They see
Yeah.
that for some reason that they can order milk online. They can see, oh, the AI can do X, Y, and Z, but they really have no idea how it got there.
Yeah.
So because AI is new and fresh, people are thinking it can do things it can't do, for example, or they
100%.
like, apply it in places it's not supposed to be used, or they find like, serendipitous uses for AI, where it's, oh, it actually really works well in this other arena. It's good to take a step back and get an understanding, get your arms around, okay, we have data science, we have machine learning, what do these things actually mean? So I thought that was actually a very good breakdown. Data science then is, like I said, businesses have these huge amounts of data. I try to impress on my students like how much data Google is in possession of, just the raw size of it and how much. Because I worked on projects where I had to track people's the heat graph on a website where it's okay, here's a mouse and they're over here 70% of the time and 20% of the time they're over here.
Yeah.
All that gets recorded.
Absolutely.
All that. You're in more in the machine learning space right now. So machine learning then, from what I'm hearing and from my understanding, essentially it's, again, you can correct me if I'm wrong here. You have a neural network, which I guess is loosely based off the way human neurons work, and that you have layers of neurons, and you send inputs into the first layer, then it performs a calculation, and then it might send inputs to some parts of the second layer, and then it will, and again, this is a generalization of my understanding, it will go up through the layers, depending, and then hit a certain spot, and then you actually can make it have a feedback where it can say, okay, cool, this is what the output I get, this is the output I wanted. Then we can tweak the equations until it gets the output that we're thinking is more realistic. So one thing you hit upon is then what sort of problems then is machine learning like showing that like real promise? Like what kind of focus does it have? Because I say that probably doesn't work for everything. Okay, but it
Absolutely
probably
not.
works really well for certain things. Like maybe it's certain things might surprise me. But what is this show like? It's shown real promise in.
I want to answer that question by backing up a little bit. In your explanation, you were talking about deep neural networks, which are one of the most ubiquitous models out there. But they're not the only model. In fact, there's, even to this day, there's like very simple and straightforward models by comparison with deep learning models that occasionally, in some use cases, actually outperform deep learning. Like, for example, naive Bayes still, which is like the dumbest machine learning model of all time, still outperforms deep learning in like language ID in some cases. Outperform, we have to like include all of the constraints, so running time and memory usage and complexity and speed and all that, as well as accuracy. Like tabular data, XGBoost performs like there's, as far as I know, and this may have changed in the last 10 seconds to be perfectly honest, there's a lot of people working on it, but as far as I know, like for a generic tabular data model, XGBoost is still best, still beats deep learning almost all the time. So we don't want to focus on one specific models. We want to focus on what is the problem here? What are we doing? Just abstractly, what problem are all of these models solving and how are they doing it?
Okay.
So here's my answer. My answer is machine learning is about constructing probability distributions using data. Okay? What do I mean by that? Take an example where someone hands you a pair of dice. You roll the dice a bunch of times. And so now you've got, first it comes up 1, 2, then it comes up 5, 6, and so on and so forth. So you just rolled this pair of dice a million times. With a million times, you ought to be able to say for each die, what is the probability that 1 comes up, and what is the probability that 2 comes up, and what is the probability that 3 comes up, right? At the outset, maybe you assume that it's a fair die, but maybe you find out that 6 comes up way more often than 2, right? So then you're like, okay, maybe I should have a model which says that the probability of 6 is higher than the probability of 2. So what machine learning is about taking some data set about these dice and trying to, from that data set, pull out a probability distribution over each die that says how likely each outcome is in practice for those dice. And when I express it that way, let's just note for a second that this problem has no solution. It's not possible to solve this problem. You don't know. No matter how many times you roll the dice, you never actually know the probability distribution. You get more and more evidence that one probability distribution is a better explanation than another, but you never actually know, right? And this is one important thing about machine learning, is that you basically never actually know the true correct answer.
I get that question when I taught math. When I was a middle school teacher, was we would do the binomial theorem and we would do dice rolling and stuff like that. And there was always the kid that raised their hand and said, "Mr. Hop, dice are not made perfectly where if I throw them, that they are perfectly random." I'm like, yes, yes, Billy, you're correct. There's probably, and so they would ask me, well, how do you calculate that? What you're saying, you're going to have to run the simulation as much as possible. But the thing is with science is that it's based on things based on previous demonstrations of those things. You don't have evidence necessarily that the next thing will 100% happen except based on previous demonstrations of it. So you only have ever really have a working model so that applies here, I guess, in machine learning is what you're saying.
100%. Yes. Every machine learning model is quote unquote just a model. It's at the end of the day, the model is as good or bad as its efficacy for the task that you're trying to solve, right? So if your task is to detect whether or not a cat is in a picture or something like that, then all you can really do is you can feed a bunch of pictures, some of which have cats, and some of which don't have cats, into the system and have the model look at all the individual pixels in the image, feed them into some mathematical formulas, and as an output it will say the probability that there's a cat in the image is like 80%, and then you have to decide whether 80% is good enough for whatever the reason why you need to detect cats in photos is. So that's machine learning. That's what we're doing. And by the way, that example that you would have done when you were teaching with binomial distributions and all that stuff, in my opinion, fitting a binomial distribution to a couple of independent random variables, if you're using an algorithm to do it, that is machine learning. You might not, maybe some people will say, oh, that's not machine learning, that's just statistics. Machine learning is solving the same problems as statistics are. Like the boundary between machine learning and statistics is not what problems you're working on, it's the techniques you're using to solve them, right? With binomial distributions, you can actually work that out more or less by hand. Maybe you can't calculate all the binomial coefficients by hand, but like the model itself, you can write down by hand. And maybe you would say, okay, that's just statistics, that's just a statistical model because you don't need a computer to fit a billion parameters. Whereas if you used a neural network or that where now you can't write it down, you need a computer to learn all the parameters for you. Maybe that means it crossed the boundary between machine learning and statistics. But anyway, point is, machine learning problems literally are statistics problems, and you solve them, the standards that you hold the solutions to are the same as the standards that you hold statistics problems to. So it's like, how accurate is my model? What's the probability of different kinds of errors? What does outlier mean in the context of this data set? What is the statistical power of the estimates that the model is making? Like any question you can ask of a statistical model is a fair question for a machine learning model, right? I think that's the most important thing to remember is, like, when we're talking about what is the scope of machine learning, we should not think of its scope as being fundamentally different from the scope of statistical reasoning more generally, with the caveat that there are statistics problems that a statistician historically would never even thought to try to solve because they just couldn't even wrap their heads around building the data sets that we have now. Machine learning has somehow unlocked our statistical creativity by giving us access to problems that would have seemed intractable and insane at any other point in history. That's really the only structural difference. And of course, like from a pragmatic standpoint, like not every statistician can be an effective machine learning practitioner because it takes a lot of engineering skills. You have to really understand how computers work and how to get the most out of them.
One of the things that shocked me was I was reading a paper. It was written, I think, in the late 70s or early 80s about how you could use statistics to determine whether or not a picture was of a certain variety.
Yep.
And the algorithm for image detection was known. They just didn't, the computers at the time just were not powerful enough, did not have enough memory, et cetera, to actually perform the operation. But the algorithm to do it was demonstrated to work. And later on, they actually used it once computers got, that boggled my mind.
Yeah, 100%. So if we go back to the specific machine learning model that you were discussing at the beginning, where you've got layers of neurons passing data from one layer to the next, that model is called the multi-layer perceptron. The original single perceptron was invented in the 1950s. That was the first time computers were less than 10 years old, and someone had already implemented a perceptron in an actual computer. So that's how far back that goes. Multi-layer perceptrons, people could conceive of them at that time, but the process of building a perceptron at that point meant actually hooking up wires from one part of the computer to the other part of the computer. So the concept of implementing one was insane. But yeah, certainly the theory was worked out in the, I don't even know, 70s or 80s or something like that. And those weren't even necessarily the most sophisticated models at the time. Hidden Markov models and probabilistic graph models were, those were in vogue in the 80s for language, and then MLPs for images and stuff like that. A lot of the foundations really have been laid for a very long time. Basically what happened is, over the past maybe 10 or 15 years, it was like a confluence of two sort of engineering success stories at the same time. One of them was high-speed implementation of certain numerical analysis algorithms. So the other part of my argument about what the scope of machine learning is and what kinds of problems you can solve with it is at the core of all of these algorithms is an optimizer. If we think back to our calculus classes that you would have taught, and hopefully most of your listeners have at least taken or heard of at one point, then a very common calculus problem is I give you a function and I ask you to find its maximum or minimum value, right?
Yep.
And the standard way of doing this is you basically look for a point where the derivative of the function is 0, and you know that the maximum or minimum value has to occur at one of those points if the function is differentiable, yada conditions. And so then you reduce it down to some small set of points that you have to check where the maximum and minimum value could be, and then you find it, right? This is all 90% of machine learning models work the same way, right? So whatever problem you're working on, you express it as an optimization problem, and then you use calculus to solve this optimization problem. Like the kinds of functions that we're talking about for a large language model or a convolutional neural network for images, they will have billions of parameters. So basically imagine you're taking matrix multiplication followed by something like the hyperbolic tangent function. So let's say those are your only two building blocks, and let's say you compose those back and forth literally a billion times. Matrix multiply, hyperbolic tangent. Matrix multiply, hyperbolic tangent.
So just one's the input of one is the output of the other kind of thing, back and forth. Okay.
Then that's mathematically that's the form that these models have. There's more too. There's also normalizations and there's dropouts, but the core mathematical structure of these is matrix multiply, hyperbolic tangent, matrix multiply, hyperbolic tangent. But you do it a billion times, right? So you're not going to apply the chain rule a billion times. You need a freaking computer to apply the chain rule a billion times, right? But that's literally what these models are doing. They're just applying the chain rule to a multi-billion term composition, okay, in order to set that derivative equal to 0 and find an optimum point. Behind the scenes, that is what deep learning is. That is what those models are doing. And it's not just deep learning, too. The other standard algorithms out there, like SVD, that's also solved as if it were an optimization problem. And so now just tying all this stuff together, if we're doing the cat or not cat example in an image, what is the optimization problem we're solving there? The optimization problem is I want a model that in a specific data set that I've prepared predicts cat or not cat correctly as much as possible. So I measure an error rate, so the number of times out of 100 that I incorrectly predict cat or not cat, and then I run my partial derivatives chain rule with a billion terms in it to try to minimize that error function. And if you minimize the error function, then you've got a good classifier that successfully predicts cat versus not cat. And to take it all home, now I can give you an answer to your question. If you have a problem and you can express that problem as an optimization problem, I can solve my problem if I can find the maximum or minimum value of some function, then you can use machine learning to solve it, or something very closely related to machine learning. If you can't do that, then you're screwed, okay? And this is if people in your audience are interested in getting into machine learning and data science, then the high-level conceptual skill that you need, not talking about programming and math and calculus and all this stuff, the high level, just put your thinking caps on, let's do some problem-solving skill you need, is to take a business problem and to turn it into an optimization problem that you can solve with calculus. If you can do that, then you can deliver just tons and tons of value to wherever you're working, right? And this is extremely difficult, right? Because let's now try to apply this to some examples. If the question is train a classifier, then according to the theory that I've just proposed, in order to turn that into an optimization problem, we just need a lot of training data, right? Because I want to like minimize the error, right? So the more training data I have, the better I'll be able to quantify this error function, and then the better I'll be able to minimize it, right? So you need lots of training data. If you can't get lots of training data, then you got to get creative and think about how you can use the training data you have more efficiently. But that's what it comes down to in the classification space. But there's plenty of other data science problems we can imagine solving. Like maybe I'm trying to like optimize sales, or maybe I'm trying to make people love my product more, right? If you can quantify if you can assign a number to how much your customers love your product on average, then you can like maximize it with deep learning, right? That's pithy, but it is that simple. Like somehow, like a lot of your job in data science is figuring out how to like mathematically quantify some like vague, poorly defined thing, and minimize the risk that customers will become enraged when they're using my product.
I have a bunch of places. Okay, I have a bunch of questions, but the main one is more of a philosophical one because, to be honest with you, this is the one that disturbs me about machine learning. This makes my ice run cold. What it's basically saying is that a lot of these things that human beings think of as intuitive, perceptive, emotional, could they be turned into optimization problems? That basically means it's that like all of these things that we thought were not mechanistic could either be copied with a mechanistic model, or they are mechanistic and we just never realized it because we don't have our brains are not capable of knowing that. And with machine learning, it's, oh, wait a second. So for example, all sorts of stuff's happening now, like video editing. The video editor is able to pick out the emotional beats within an interview and turn them into short clips ready for YouTube with a click of a button, right? Absolutely terrifying, because I'm saying, in order for me to know whether or not a part of a video had emotional impact would mean that a human being has to sit there and say, okay, cool, I'll watch this hour-long video, I'll record whether or not I felt something, and then we can train the machine learning model to reflect that, and then that means then that my feeling of being impressed or in awe or anything is actually something as predictable. If it's predictable, then it's mechanistic on some level. Am I being like, because what it means is that leads into a whole other space of then if things are mechanistic, then they're understandable to a point, depending on our ability of technology. If our ability of technology gets to a certain point, we will be able to understand and control a lot of things we were not able to do before.
The way I'll go about this,
off in the deep end.
I will start off by comforting you and being like, don't worry, John, it's not that bad. But then I'll go back to being like, but maybe it's that bad. We're going to go through that journey, all right?
Okay, gotcha. So, thank you for warning me.
I think a good way to feel not as bad about it is to pause for a moment and imagine that you were put in a position where you're working for this company and they're like, John, I'm sorry, but I hate to do this to you, but you have 2 weeks to come up with a find the emotional beat model in video. I'm sorry we didn't tell you this sooner, but this is the way it is. So now you're in this position where you're panicking and you're like, oh my God, this is not possible. What am I supposed to do? Once you get through the panic, you'll start to come up with some ideas, right? So one idea you might come up with is like, when the volume goes up, then maybe that means people are shouting. So then maybe that's an indicator of emotional intensity. Another one might be, if there's a lot of motion in the screen, then maybe I'm like waving my hands, and that could be an indicator of emotional intensity. Or maybe you would have a speech-to-text thing that would be looking at language, and you could start imagining linguistic features. If there's more swear word, if you just sat down and just did a little brainstorm amongst yourself, you'd probably find 5 or 10 pretty good predictors of emotional intensity. Are they going to be perfect? Of course not. But also, let's think about the user experience here. User experience, they're probably not setting the expectation that they have the perfect answers here. Instead, they're saying, we think here's some possible places where there might be some emotional intensity in this video. You should go check them out, right? So they've made their problem easier. They don't have to be perfectly accurate. They just have to provide enough good suggestions that you don't feel frustrated going through a bunch of false positives and false negatives, right?
Right.
So now, as you think about it, maybe we don't even have to use machine learning for this. Maybe we don't even have to perform this task of gathering a bunch of videos and classifying each moment according to emotional intensity. Maybe we just take some heuristics and evaluate those heuristics on some validation data or something like that, but then try that out and see how customers respond to it. If you're a machine learning practitioner, you should go through this process before you use any machine learning model. I have a task to find cats in pictures or estimate the sentiment of social media data or something like that. The first thing you should do is you should think of just some heuristics in your own head that you think will be good predictors and just try them out. And if those are good enough, then you can ship your product without doing any work and you can go lie on the beach. If they're not good enough, you'll have articulated the complexity of the problem a little bit more. You'll realize that it's not just some simple heuristic that's going to solve your problem. You know that you need some kind of model that's complicated enough to make certain kinds of distinctions, but not other kinds of distinctions. My prediction with this very specific feature is that you could do a really good pass at it without any serious machine learning. And so then that's not so scary. Now we're just saying, okay, high volume is an indicator of emotional intensity. That doesn't mean we're all automatons from Blade Runner or something like that. That just means that human behavior is maybe not totally predictable, but it's also not completely random. That's all we're saying here, right? That's not so bad. Yeah, we feel good. All right, now let's feel terrified again. The reality of it, though, is that in a lot of cases, and we've especially seen this in the context of human language recently, like human language is the thing where, like, you would have imagined, or I would have imagined, that it's like pretty much impossible to come up with a system that can capture all of the nuance of human language. And to be fair, we've not captured all of the nuance of human language. It seemed outlandish as recently as, I don't know, maybe 10 years ago, that we would be able to build a model that could read every book and every tweet and every Facebook post ever written, and then make that knowledge available to you in a conversational interface. Because it just seemed like the degrees of freedom in that probabilistic modeling problem were too high, right? Like it just feels like there's an infinite number of variables that you have to get right. But what we found is that there weren't an infinite number of variables. There were only like 500 trillion variables. And 500 trillion variables is like in reach of modern computing, right? And so we could find the same thing out about the human brain. It feels like human behavior and human emotions and all this stuff, it feels like it's an infinite number of variables. But maybe it's only 500 quadrillion variables, and maybe 500 quadrillion variables are only 10 years of hardware engineering away, right? So we have to acknowledge the possibility that, yeah, like maybe we're a lot less random than we think we are. It's possible. We'll find out. People are going to work on it, so we're definitely going to find out.
People are definitely working on it in a lot of different spaces, but I think that it's an important point because it dovetails earlier where we had the idea, we just didn't have the technology to actually go through with it. And as it like pushes forward, it's going to be, like you said, I would tell students like a math problem, if they're trying to find like local maxes and minimums, they may not be global maxes and minimums. So you may have to like necessarily zoom out and be like, oh, wait, we're not actually the bottom of the hill. If we go over the next hill and go all the way down, that's the actual bottom of the hill. So that's
a real problem. Yeah. Absolutely.
Yeah, that could be the thing here. We just don't know necessarily until we actually try.
Yeah, the other thing I would point out is the kind of thing we're talking about here. Can we build a model that, in some sense, accurately represents or simulates or something human behavior? This is not a thing that we can really express as an optimization problem, right? So if I give you a machine learning model that produces text, maybe produces images, is like an attempt at representing the complexity of a person. I can't come up with some like universal metric that's going to say this is how close that system is to being a person or being person-like. That's not a well-defined concept. There's probably 1,000 philosophical questions that you have to get through before we even really have a well-defined problem. And if you don't have a well-defined problem, then you probably can't solve it with machine learning, right? So that's another kind of issue. When people talk about things like the singularity and human-like AI and will AI destroy us all, there's something missing in all of these conversations for me, which is just the foundational definitions. It's what does intelligence actually mean? Like, how do you measure it? That's not a problem we can answer for humans, and if we can't even answer it for humans, it means we don't have a definition. It means we don't have an optimization criterion. So there's no way that we're ever going to be able to definitively say that this thing is more intelligent than that thing. Maybe by accident, but also a lot of these kinds of notions like intelligence or like humanness or anything like that, these are also all very subjective. When we get into this more philosophical territory, the question I always want to ask is, what are you really talking about? What do you really mean? What are you really asking? What prediction do you actually want me to make here? How will we know if we have met your criteria for the singularity or something like that? So that's one consideration here. And then I don't know if the thing I'm about to say is actually directly going to answer any of the questions you've asked, but I think it's just a relevant thing to say. There's a tendency that I don't like to communicate badly about agency when we start talking about AI. So what I mean by this is you often will see headlines or people just ranting about how AI destroyed the stock market or an artificial intelligence system screwed up and killed 5 people by crashing into a pedestrian. Imagine writing a similar sentence with any other kind of technology, right? If a person gets drunk and hits someone with a car, they don't say car killed pedestrian, they say drunk driver killed pedestrian, right? It was the human driving the car that killed the pedestrian. If a stock market trader makes a really risky bet and loses $1 billion, they don't say Bloomberg terminal loses $1 million. They say person using the Bloomberg terminal lost $1 billion, right? And this is the language we should be using with artificial intelligence too, right? So if we ship a self-driving car system, like an AI that can drive a car for you, and if that car hits a person and kills them, like it's a misnomer to express that event as an AI system killed a person. No, the cause of that person's death was an engineering team working for an automobile manufacturer built a system, built a car, and that car had, as part of its design, the risk built into it that it was going to kill a pedestrian, and that risk was realized. And that's what you have to talk about. You have to talk about, did the team that built that car, did they behave responsibly? Did they make correct decisions? Were the risks acknowledged? Were they measured correctly? Were they following regulations? These are all the questions we need to ask, right? And I think this is just the right moral framework in which to talk about artificial intelligence as of right now anyway. We're not at the point where it really makes sense yet, anyway, maybe someday, but it doesn't really make sense yet to think of an artificially intelligent system as having agency or being accountable for its behavior. At the moment, I think the correct thing to do is to think of humans as having the agency and humans as having the accountability, and an AI is just a tool, and we just evaluate AI systems according to how good they are as tools.
As we do with all our other tools.
That's it. Yep.
Okay. Let's shift gears a little bit here because I want to talk a little bit about how you get into this field because I don't know very much about how to get started. I can get someone to be like a back-end developer, a front-end developer, working for like maybe like a FANG or medium-sized company. I don't work with large data sets. I work with SQL, but I don't analyze anything within them. It's more about getting things in, getting things out, making the screen look pretty. Am I using the right algorithm and analyzing it? My level of math is usually, people are always like, oh, you're a computer programmer, so you must know math. I'm like, the highest level math I use during my daily job is 7th grade, like percentages and fractions. Like that's the highest we go. Like big O notation is like flirting with limits, but not
Yep.
really. And that's about it. I don't have to touch like linear algebra. I don't have to do partial derivatives. None of that stuff. Like, where would you get started if you were like today? What would you tell someone like, hey, I want to get into data science, but I want to get specifically into machine learning? Where should I start? What should I start learning? What competencies am I going to need to start working on so that a year or two from now I'm in the thick of it, I'm employable, I'm working on some grand, I don't know, project to send someone to Titan or whatever the next thing is going to be? Like, what would you recommend that they start off with?
This is a good question. The way I'll answer it is I will say what I think the core competencies in this space are. And there's a joke, which is that machine learning or data science or whatever is 50% engineering, 50% math and statistics, and 50% domain knowledge. And of course, that adds up to more than 100%, which is what it feels like most of the time. So you need a little bit of each of those three things. So let's just talk about what I mean by those three things. So when I talk about computer programming, I don't just mean like programming, but software engineering more generally. Things like certainly how to code, but also like how to deploy code into production, how to maintain code, how to communicate with business stakeholders about code and engineering and stuff like that. Just all of the stuff that is involved in a software engineer's day-to-day. A data scientist or a machine learning engineer is going to encounter some or all of those same considerations. Usually not the same, but very similar at the very least. And it depends on the job too. Some will be more engineering heavy than others. Okay. Math and statistics. What do I mean by that specifically? For machine learning purposes, probability theory isn't, I don't pretend I didn't say theory. Probability, then statistics, which is like a very close relative of probability, or it's applied probability essentially. So we're talking things like what is a hypothesis test, what is a p-value, what does independence mean, all those kinds of things. Those are very useful in your day-to-day. How do you measure the accuracy of a model? That's a harder question than you might think at first. So just like good statistics sense for how to talk about models, how to evaluate models, that kind of thing. Then on the domain expertise, now this depends on your area. It's very difficult to do any kind of problem solving in any area purely abstractly. So my background is I have a PhD in math. I did pure math for many years. And that equipped me to solve problems and equipped me to think abstractly, but it did not equip me to work with social media data, which is my last job, or to work with food science, which is my current job. I've had to learn in both cases a lot about marketing and food science and Bayesian analysis and all sorts of stuff, right? So it's whatever problem space you're working in, you're going to, at some point, need to develop some knowledge about that space. Okay, so those are the core competencies. So now let's ask, how do you break into machine learning, all right? So it depends on your starting points. Let's say you're starting out as a software engineer. So you've been working as a software engineer for 5 years, and you're saying, hey, man, this machine learning stuff looks really cool. Then you're like really good on that first competency. You're like starting with a really good engineering background. So you need to focus on the other two. If you are happy to trying to do machine learning in the domain where you already work, where you already do software engineering, then maybe you've got the domain expertise covered too. Now you just got to go learn some probability and statistics, and that's where you need to fill the gaps. Oh, and the math and statistics section, I should have included calculus in there as well. You should also know, you don't need to know thoroughly, but you need to be conversant in the notation of multivariable calculus. I would say you need to know.
Calc 3.
Yeah, through Calc 3. In most universities, it's Calc 3. So we're talking partial derivatives, total derivative, chain rule. That's kind of it. And if you already know one variable calculus, then learning that stuff is honestly not that difficult. You just hold all the other variables constant and do the one variable thing, and that's a partial derivative. That's it. I just taught it to you. Good. Yeah, you learned something in this podcast. Fantastic. So by contrast, let's say your background is you're a scientist, right? So maybe you're working in, I don't know, biology or physics or something like that. Now, if you can if you're interested in a machine learning job in your area of expertise, if you're a biologist and you're interested in pharma, now you've got the domain expertise covered, and through your scientific training, you probably also have most of the math and statistics and stuff like that. So now you got to practice the engineering. So now you got to learn how to code, and you got to learn how modern software engineering works. Again, not to the level of expert, but you got to learn something about it, right?
Right.
So this is, I think, the way you figure it out. So you figure out where your competencies are, and then you try to learn something about the other competencies. And from the perspective of a hiring manager, like a hiring manager in machine learning, most of them are not going to expect that you're going to excel in all of those areas. Most of them are going to expect that you're going to usually come in strong in one area in particular, and then they expect that you're going to have to beef up on the other two areas. And that's usually fine for at least a junior machine learning or data science position. It's usually enough to just be able to have one competency and then being able to demonstrate that you're willing and able to learn the other competencies. The last thing to say to address your question is what happens if you've got nothing, right?
Right.
There's a lot of people who are really interested in AI and machine learning now because it's getting a lot of buzz. And they're like, man, I'm working in some other, maybe I've been a musician my whole life, but man, this is really cool. I really want to learn this stuff. It's the thing I want to sell you on is you can absolutely do it. It's way more attainable than you might think. What I mean by that is, if you're in that position where you're not like ready to apply for a job right now because you know you got to learn something, but you just want to break into the space and see what it's like, you can toy around with these tools without knowing anything. And I should back off of that for a second, right? Because you're probably going to need to like
Qualify it, but
be able to like you're going to need to spend a few weekends learning the basics of Python, but I really mean the basics of Python.
oh,
And
Python
then
takes 10 minutes. It's really easy.
as far as programming languages go, it's not going to take you more than a few weekends. When I say that, I know there's going to be someone out there who's going to go through it for a few weekends and be like, "Oh my god, I'm an idiot!
Oh,
I
there's a
still don't get it."
keyboard warrior right now. He's coming right in the comments.
Yeah, exactly. So this is a probability distribution, but it's like the skill you need. What I'm really trying to say here is the skill you need is not like the mental acuity to pick up programming quickly. You just need perseverance. I would say most people can pick up enough programming in order to crack into machine learning without spending years and years training. It just takes perseverance. That's what it takes. It doesn't take any like deep understanding of engineering or anything like that. So, like when I say there's these online courses out there, like Fast AI is a really good one. There's some on Coursera, and they start you off with like very little background knowledge. They don't assume anything about math. They don't assume anything about statistics. They're like, in order to run any of the examples, you need to like have some basic skills in Python, and that is it. That is literally the extent of it. And yeah, like you can get started and you can try these things out very quickly. Are you going to be an expert practitioner after just tinkering around with some existing models? No, you're going to need to go and do some study. But don't let the stuff further down the path discourage you from giving it a shot. You would be shocked at how fast you can get up and running with some of these tools and just trying stuff out. But I guess the last thing I'll say about this is when I talk to other engineers about this, and the engineers tend to be most intimidated about the math stuff, like the probability and the calculus and so on. I'll be honest with you, you could probably ship an end-to-end machine learning system that does something cool and interesting knowing only software engineering and zero math. If you like literally don't know what a probability or what a partial derivative is, and you don't really feel like you understand probability all that well, for your first demo machine learning project, it wouldn't hold you back in the slightest. You would never even encounter it, in fact. It's only for like when you need to troubleshoot these things, or if something new is released and you want to understand what it's doing, or if you want to tweak an existing thing to solve a related problem, then you got to be able to read the papers, and you have to understand understand the papers, and you have to understand what the numerical optimizer is doing. Here's another thing about deep learning. Most of deep learning is really just like tricking a gradient descent algorithm into converging faster. That's it. That's really what it's all about.
You're gonna have to unpack that sentence a little bit for me.
Yeah, okay. We're just taking the derivative and setting it equal to zero, right? Setting it equal to zero, then solving equations. That's what you do in a calculus class. You set the derivative equal to zero and then solve some equations. We don't do that in machine learning. Instead, we have an algorithm that starts with some point, and it slowly starts marching towards the point where the derivative is equal to zero. That's what it actually does. And
Okay.
that's called gradient descent. It should be called gradient ascent, because usually you're going up, but mathematically it goes down for whatever reason. You find some minima rather than maxima, whatever. It's called gradient descent because you're just descending along the derivative, aka gradient. And it does it by jumping around in certain ways. And most of the time when you're trying to debug a machine learning algorithm, like if you're not getting good answers or if it's just not working correctly, most of the time it's because you haven't figured out the right parameters for this algorithm that kind of like tries to converge on the point you're looking for. So if you get into that kind of business, then it helps to know something about the calculus. But for your first project, you'll probably never encounter that. For your first project, like if you want to just train a classifier, you can just do it and it'll work and it'll be fine and it'll have fun.
Wow. So that makes me wonder then if there's going to be like a moment where, for example, in most modern programming languages, they have a garbage collector. So like when I was like 14 years old, 15 years old, I was doing like C and C++. you had to manage your own memory. Like alloc and dealloc, it was like a nightmare. But it made you think about memory usage. You were forced to because in the olden days, memory wasn't as plentiful as it was now. And some kind soul came up with a garbage collection algorithm and said, for better or for worse. And now I tell my students that they don't have to deal with that. Like when they program in C Sharp, they don't even need to know, for example, the variable that they make is actually being held in memory somewhere, and how much space does it take, and is it being like used or not. You can make web apps that probably spend memory like a drunken sailor, and they still work just fine, and the end user has absolutely does not care at all. They could be totally optimized, but you don't know any of that's going on under the hood because someone basically worked it out for you. It's automatic. And do you see that happening with machine learning, where it's going to be like some of this stuff is going to basically turn into predictable patterns that can be packaged and put under the hood, and then someone can just use them?
Yes, this has already happened in two ways, and I'll tell you about both of them because it's fun. The first way that this has happened is it used to be true at the beginning, and here I'm talking mostly about deep learning stuff, but it used to be true that in deep learning you had to compute your own derivatives. And what you'd have to do is you'd have to explicitly calculate the derivatives and then write functions in Python or whatever your programming language is that compute those derivatives, and then you could use a numerical optimizer to set the derivatives equal to 0. That was the chain rule plus set the derivatives equal to 0, essentially. That was the old way of doing it. We haven't been doing that for 10 years now. Now there's two very standard, very popular, extremely well-built frameworks called PyTorch, which is what I prefer, and that's built by Facebook/Meta or whatever they're calling themselves, and TensorFlow, which was built by the folks at Google. There's the technology is called AutoGrad, and AutoGrad just means you just write your functions and we'll handle the derivatives for you. You just don't worry your pretty little head about it. And this is utterly fantastic. So the reason why I can tell you that you can get started with machine learning right now without knowing any calculus is because AutoGrad will just do it for you. So that's just a miracle. It's fantastic. Like whether you're a PhD in math or whether you don't understand multivariable calculus, it is so much nicer to not have to worry about your own partial derivatives. I can't even tell you. So that's thing one that you don't have to worry about. And the other thing you don't have to worry about is the models themselves. You often don't have to train your own model from scratch. The modern way of doing machine learning is someone else. Okay, let's back up. So how did things work in an eternity ago of 2015 when I started doing machine learning? So let's say I wanted to solve like a language classification task in 15, sorry. What we'd do is we'd get a big training set. It would be like, here's a bunch of paragraphs, and then here's the class label I want to apply to those paragraphs. So it could be like, maybe I'm trying to do like a domain categorization thing. So this paragraph is about politics. This paragraph is about science. This paragraph is about comedy. Let's say that's the task. So I'd get a bunch of data that would have these paragraphs, and then I'd have the labels, the correct labels for what the category is. So what would I do? I'd chunk out a portion of that data set that I would think of as the training set, and I'd use the other part for validation. I would break up the text into tokens. So in other words, I would isolate individual words from other words. Maybe I would do some manipulation with those tokens. For example, if I might want to consider the word apples to be the same as the word apple because they're both just apple with different tense or something like that. And then I would fit some model, like maybe a linear model or some other kind of model that just tried to predict an output label given some sequence of tokens. And that's it. That's how I do it. And you can get pretty far. If you have lots and lots of training data, so you have lots and lots of examples of input language being mapped to output categories, then you probably have enough information to find some patterns. Or a model will help you find those patterns, of course. That's not at all how you would do it today. The way you would do it today is you would download a large language model. There's a lot of very high-profile ones like Llama and the GPT family of models and so on, but there's also models that Google have built like BERT. Basically, what these models do is like somebody very wealthy with like literally tens of millions of dollars to spend have said, what we're going to do is we're going to build a universal model that can solve, that just understands all of human language really well. And they train that by taking billions and billions of documents and feeding them into models with billions and billions of parameters, and they get this just like mega thing that just knows all of human language. So now how would I solve a language classification task? I would download that massive thing, and then there's like various different strategies for feeding your training data into that massive thing, and just be like, all right, like here's my task. You know everything, so you go solve my task, please. And it does it, and you win. And that model like outperforms the 2015 strategy just by orders of magnitude. Basically, it's like this. It's like if you want to solve a text classification problem, that used to be you just have to get a lot of examples. Now it's like you first try to understand all of human language, and then you solve this problem as a special case of understanding all of human language. That's the way we do it nowadays.
That's a weekend project. Like all human language is a weekend project, something light.
Yeah, it's like the building the models to understand all of human language, that costs tens of millions of dollars and thousands of hours. I don't know. You can build like a pretty mediocre large language model in a few weekends if you've got a GPU lying around. But the real point is I have one that someone else made on my computer right now. I don't know exactly why they're all just releasing them publicly, but it's Facebook and Google just have more money than they know what to do with, so they spend $50 million building these things, and they just put them on the internet, and now you can use them. That's it. That's how you do it.
I guess long term it furthers the overall science of doing it, because to give an analogy with programming, which is what I understand, a lot of things I do, and my students are shocked, I don't program, for example, a PDF writer to take the screen and turn to a nice pretty PDF. I didn't write that code, and I probably could do it, but I want to just go on to NuGet and download a pretty PDF, and then it does it. So it's like, why wouldn't you do that? Because there's a certain point where you should do that, because the person who did it has spent hours and hours optimizing it, which is hours you don't have to spend doing it. So it sounds like it's the same pattern. Someone's already spent a gajillion hours optimizing for this problem, and then they're basically saying, here you go, kid, knock yourself out. And why wouldn't you use it?
100%. It's a weird situation we're in where like all of this stuff is just out there and available. State-of-the-art tools are just out there and available. And the economics of that are still confusing to me, but right now, woohoo!
All right. Last question before we wrap up. This is more back to being philosophical.
Yeah.
Do you think that we could build general artificial intelligence?
It goes back to my previous answer. I need a precise articulation of what it actually means, like what the success criterion are, in order to be able to provide a good answer to that question. I think if I'm just thinking about that question in my own head, if I'm being completely honest, I don't spend much time thinking about that question, because for me it's more interesting to say, here's a really hard problem, how can I solve it? That's what gets me going, right? But it is fun to think about these things from time to time, so I have thought about it. So what's my answer? So my answer is, like, when we say artificial general intelligence, I think what we mean is a model that can do a lot of things that it maybe wasn't necessarily trained to do. It's a single model that can generate language, and it can drive a car, and it can trade in the stock market, and it can understand patterns and images and so on. Will we ever have one model that can do all that stuff? Okay, so now I have two answers to that question. The first answer is there's a very boring way of doing that, which is you think of like all of the tasks that you want this model to be able to do, and you build models that do each of those tasks, and then you effectively duct tape them together. Done. Katamari Damacy. You played that game back in the day, right?
Yeah.
Do that. Do a Katamari Damacy of models. That's not a satisfying answer, though. Like, that's not what you asked. You're not like, Paul, do you think you could duct tape a bunch of models together? That's not what you were asking. You were asking, is there some, I don't know, magic to the universe that prevents us from mathematically modeling everything? Or is it all just going to be math at some point? So let me try to answer that question. That's maybe the more interesting question. The answer is, of course, I have no idea. And I also still think, even as I've broken down the problem a little bit, there's still a lot of details to be worked out about what we really mean here. But what I will say is, I think there's a big conceptual hurdle, like a major technical hurdle that has not been overcome in the current AI literature. And that technical hurdle is, can we build a model that's designed to do one thing and teach it to do a completely different thing, right? Like when we build language models, we train it on a bunch of text data. When we build image models, we train it on a bunch of image data. A good question would be like, could I take a model that is trained on image data, and could I somehow fine-tune that thing to be really good at language, right? Is it the case that having a model that's really good at working with images is like most of the way there towards being a model that's really good at working with language? The answer is I don't think anyone knows. I've never seen like a convincing example of that happening. It could exist, but I haven't seen it. We have models now that are good simultaneously at working with images and text, but the way you build those things is you essentially like you do the duct taping thing I was talking about.
Just
Right?
graft them together.
It's not like they built a model that learned that knew how to do one thing and then it somehow learned how to do something completely different. And it's a very like elementary example of this if you're looking for a side project, John, hint hint. Be like, here's a really interesting task that I don't think anyone knows how to do, and I think it would be really interesting to try to solve this. So there are AI models now that have vast superhuman capacity in the game of chess and the ancient Chinese strategy game of Go. Which, have you ever heard of Go, John? You know about that one?
Oh, I think I've heard about it. Yeah, something
Heard
about
of
it.
it? Okay.
It's like
Anyway,
a board
I'll let
game.
you look up the details later. But anyway,
Yeah.
so right now we have AI models that can just like beat those two games. They can beat any human in either of those two games.
Oh, yeah.
And actually, both of those models use the same kind of techniques. They use like reinforcement learning plus neural nets or something like that, right? But what I haven't seen is, could you build a model that's really good at chess and somehow fine tune it to a model that's really good at Go? I don't think anyone knows how to do that. And if you could figure that out, I think for me, that would go a long way to convincing me that something like whatever we mean by artificial general intelligence is possible. That would mean that we've got models that are not just trained within their own scope, but that can move outside of their own scope. They're like more like abstract problem solvers that can handle lots of different kinds of problems rather than just one.
That's our brains, right? That's an analog
Yeah,
for the human brain. Is you can give the human brain enough time, and it learns a language. It solves
right.
tooling. But then, and this the exact our ancestors' brains are not really built differently than our own.
Right.
It's just times. One of the history questions to ask kids was like, okay, let's take someone from 5,000 years ago and bring them today. It would be, they thought about it. They were just like, well, wait a second. If I just they could learn to use a phone. They could maybe even learn to drive if they're young enough. Like, they just didn't have those opportunities. So the brain is like very malleable. Like, it's just a
That's
network, and
right.
I can go ahead and build a road just as well as I can build a computer. Some people better than others. So that from you, that would be more of closer to some definition of general intelligence, where it's like, hey, here's something novel. I'd like you to solve it.
Yeah, exactly. So some new problem space. Can you handle it? And it's very hard to define new in that case because certainly within a domain, right? What we found with large language models is that I never trained my large language model to build a sentiment classifier or to do some other kind of text classifier, but somehow its general understanding of language is enough for it to be able to solve each of those individual problems, even if it had no idea that was going to be a problem it encountered. So there's a little kernel of it there. But what would it mean? What would it even mean to build a data set for artificial general intelligence, right? What would this thing be trained on that would allow it to solve all, like both text problems and image problems and games and stock? There's no data set there, right? So somehow it has to be like some kind of algorithmic or cognitive, for lack of a better word, capability that I don't think we've built in a computer system yet. I haven't seen an example of this that convinces me.
Okay. This goes back to my deep-seated fear that there is the equation for us. You know what I'm saying? I'm going to get to the pearly gates. They're going to be like, here is the John Hoff equation. Running these numbers and variables just laid out your entire life. You will never escape the bounds of this equation. That's what keeps me up at night.
So this idea of just grafting a bunch of models together is people are going to do this, right? So we're going to get these systems that, from the perspective of a user or someone who's like looking at the system, can do anything, right? IBM's Watson was designed to be like this, right? The vision for IBM Watson is like you started off with some task, but if there's a thing that you wanted to do, it doesn't do, sorry, then you just acquire whatever startup is doing that well, and then you just stick it in behind an API endpoint. And now, as far as anyone else is concerned, IBM Watson can now do that new thing, right? So we'll be able to do that. And so we're going to get to a point where there's like systems that certainly from any reasonable perspective just feel like they can do everything. And maybe that's enough. Like maybe that will cross the artificial general intelligence boundary for most people, right? Because who cares what it's doing from an internal perspective? But would that be like the John Hoppe equation or like the knowledge equation? Would that really be like I don't know. Because it's hard to answer this question even about humans. Because we know that for humans, we've got like language processing centers in our brain and we've got image processing centers in our brain. So we know that our brain is actually like a Katamari Damacy of models already, right? So maybe that is the universal truth, is like there isn't one simple 2-line equation where you witness it in all of its glory and then spend eternity marveling at its beauty or anything. But maybe it's just like the world is complicated, and so you need a lot of pretty complicated models just combined together to grapple with it. Maybe that's the truth of existence in the universe. Who knows?
Like, this got really deep. By the way, this has been an absolutely fascinating conversation. Hopefully people watching this will get into data science. Like you said, you were able to break down the 3 domains. Python. I'm going to do a tutorial video on Python to help people get started. All right. Thank you very much, Paul. This has been an absolutely fascinating conversation. So again, you can subscribe down below if you'd like to hear these kinds of conversations. And thank you for talking with me.
Thank you very much for having me, and please invite me back some other time.